Welcome to AI Paper Slop. Today we are diving into Gated DeltaNet-2, Decoupling Erase and Write in Linear Attention by Ali Hadamzadeh, Yejin Choi, and Yang Coates from NVIDIA.
Right, and we're just going to give you the punchline right out of the gate.
Exactly. So for the AI researchers and ML engineers out there, linear recurrent attention solves the quadratic scaling cost of transformers.
Yeah, but it suffers from severe memory interference when you push it to long contexts.
Right.
Past delta rule models, like KDA, used a single scalar gate to control both forgetting old info and writing new info. Gated DeltaNet-2 completely fixes this bottleneck by decoupling the edit.
They introduce a channel-wise erase gate for the key axis and a channel-wise write gate for the value axis.
And at 1.3 billion parameters, this architecture just thoroughly beats Mamba 2, Mamba 3, and KDA on long context retrieval.
Especially on those multi-key needle-in-a-haystack benchmarks.
Oh, absolutely. And it retains high H100 trading throughput via a novel gate-aware chunk-wise WI algorithm.
Yeah, so you get surgical memory editing without sacrificing linear time efficiency. But, to really get why this matters, we need to look at why the previous state-of-the-art was failing.
Well, it all comes down to the fundamental compromise of linear attention. In a standard transformer, you have this explicit attention matrix.
Right. Every token gets direct access to the entire history.
Exactly. The compute cost scales quadratically, but recall is perfect. Linear recurrent attention avoids that by compressing the sequence into a fixed-size key-value memory matrix.
Which is great for the compute budget, but that compression creates a massive problem.
Right, because exact retrieval is incredibly hard when you have millions of associations sharing the exact same finite space.
It's all superimposed.
Yeah, you try to recall one fact, and you get interference from 1,000 others. So prior art tried to give the recurrence mechanism more control over what persists in that state.
And we saw Mamba 2 introduce global scalar decay.
Right, to regulate the memory horizon.
Yeah.
And then DeltaNet introduced the delta rule for targeted overwriting.
Where it basically subtracts the current read before writing, right?
Yes. And Gated DeltaNet combined global decay with that targeted edit. Finally, KDA, or Kimi Delta Attention, replaced scalar decay with channel-wise for getting over the key dimension.
Okay, let's unpack this, because this is where the previous models hit a wall. KDA gave us channel-wise decay, but the active edit still relied on a single scalar gate.
Yeah, usually denoted as beta T.
Right. So picture a densely packed whiteboard with all your context for a problem. You need to add a new equation, but you have to remove an old one to make room.
I like that analogy.
But the catch with KDA is that you're forced to use the exact same pressure to erase the old equation as you used to write the new one.
Right, you can't just delicately wipe away a tiny mistake and boldly write a large correction.
Exactly. Why did we ever think one scalar could control two fundamentally different operations, removing stale read coordinates and committing incoming value coordinates?
Well, it was just a simplification. Erasing is a key-side operation, deciding which coordinates of the old read to remove. Writing is a value-side operation, deciding which coordinates of the candidate value to commit.
They live on completely different axes.
Exactly. Tying them wasn't mathematically required by the delta rule, it just severely bounded the expressivity of the update.
Which brings us to the core innovation here. Gated delta rule 2. They take that single scalar and mathematically untangle it into two independent vectors.
Yeah, you get an erase yet, BT theta, applied to the key coordinates.
And a write gate, WT, applied to the value coordinates.
What's fascinating here is how this connects to the fast-weight memory perspective. The update is actually an online gradient step on a local regression loss.
Wait, really? What is the model trying to minimize there?
At each token, it minimizes the difference between the new state and the decayed memory, but it subtracts the current read along a highly specific gated erase direction.
So it's not just a blanket subtraction.
No, the direction is your erase gate multiplied by the current key. Then it writes toward a gated value target, which is your write gate multiplied by the current value.
So if you picture the model processing tokens, it's making these split-second, channel-specific decisions.
Exactly.
It clears broad context through decay, surgically removes selected stale associations through the erase gate, and specifically inserts only the value channels that matter right now.
It's highly granular. It's saying overwrite these specific features, insert these specific new attributes.
That is incredibly precise, but elegant math is useless in modern ML if it doesn't run efficiently on a GPU.
Oh, for sure. You have to use parallel training.
Right, so how does this decoupled math survive the parallel training requirement?
They use a chunk-wise WY algorithm. The sequence is split into chunks of usually size 64.
Okay, so interactions inside a chunk are dense matrix products.
Exactly, which tensor cores love. And recurrence only happens across chunks. The genius here is how they absorb cumulative channel-wise decay into rank 1 erase factors.
Creating a compact WY representation.
Yes, which requires a small forward substitution, like a triangular solve, inside each chunk.
Wait, if you decouple the gates from a simple scalar into channel-wise vectors, doesn't that completely break the standard backward pass?
This raises an important question. Yes, it breaks standard scalar post-scaling.
Because you can't just factor it out anymore.
Exactly. In KDA, you could apply the scalar factor after the dot product. But here, the gates are diagonal matrices over different channels.
So you're stuck.
Well, the gates must now be baked directly into the dot products during gradient accumulation. The authors built a completely custom gate-aware backward pass for this.
And it barely impacts throughput, right?
It's wild. On an H100, training speed only drops mildly from 38.0 thousand tokens per second for KDA to 36.1 for Gated DeltaNet-2.
That is a near-flat scaling profile compared to the sharp degradation you'd see in standard transformers.
Yeah, you pay a tiny constant overhead for vastly superior memory control.
Here's where it gets really interesting, though. How do you build a full language model out of this?
They tested two families, pure recurrent models and hybrid models.
And the recurrent block design has short causal convolutions, SILU, and L2 normalization on the queries and keys, right?
Yes, the L2 norm stabilizes the scale. It prevents the values in the recurrent state matrix from exploding.
But the hybrid approach is just brilliant.
It really is.
They pair the Gated DeltaNet-2 token mixer with sliding window attention, or SWA.
SWA acts as this high-fidelity short-term memory for exact local interactions.
Like shifts and comparisons.
Exactly. Well, Gated DeltaNet-2 acts as the compressed, massive long-term memory for, say, 100 billion token history.
So you have the math, the kernels, the architecture. Does this 1.3 billion parameter model actually beat Mamba 3 and the rest?
Yes, they tested it on 100 billion fine web edu tokens.
And Gated DeltaNet-2 achieves the best averages across Wikitext, Lambatak, and commonsense reasoning like PQA and HeliSwag.
It beats Mamba 2, Mamba 3, SISO and MIMO, and KDA. But the most critical victory is on the ruler, needle, and a haystack benchmarks.
The multi-key tests, right?
Yeah, MKNIAH. Here, the fixed size state must separate competing associations.
And decoupling erase and write is the exact mechanism needed to survive that interference.
Absolutely. It also dominates real-world recall tasks like SWDE, Squad, Trivia QA, and Drop-E.
So what does this all mean? Which gate is actually doing the heavy lifting?
The ablation studies show the erase gate is the absolute MVP.
Right. If you remove the channel-wise structure from the write gate, performance drops a bit.
But if you remove it from the erase gate, performance tanks completely.
Wow. So decoupling the scalar tie allows for this surgically precise memory editing, vastly improving long context retrieval.
All while keeping that linear time efficiency.
Which is incredible.
It really leaves you with something to mull over. Since the erase gate is doing the heavy lifting, it suggests that forgetting is actually more important than learning in compressed memory states.
That completely flips how we usually think about training.
Right. What if future architectures stop relying on self-supervised next token prediction to learn what to forget?
And we start explicitly supervising the erase gates.
Exactly. Could mastering artificial forgetting be the final key to unlocking infinite context reasoning?
It's a fascinating thought. Thank you for joining this deep dive on AI Paperslop, and keep diving into the data.